Federal Reserve Bank of New York, Ethan Madeline, and will tell us about online estimation of macroeconomic models.
Hey everyone, so I'm going to be talking about the estimation method that we're using that makes possible everything Rika just talked about. If you were here for our talk, that's great, you know about DSG models. If you weren't here for a talk, that's totally fine because sequential Monte Carlo is just a way to sample from an unknown posterior, and you can use this for any model. And I'll be talking a little bit about that, but obviously I'm an economist, I'll be talking mostly about economic applications. What do I mean by online will become clear as I sort of talk, but that's one of the really cool things, in addition to estimating these big heterogeneous agent models that we think is pretty nice about this algorithm. It's based on a current paper that we're working on with Rika, who just presented, my boss, Marco Del Negro, and then two external collaborators, Ed Herbst from the Fed board, Frank Shorfida from University of Pennsylvania, and Michael Kai, who just finished working for the Fed, is now going to Northwestern. Finally, these views are my own. I'm speaking for myself, and you can read the disclaimer. Okay, so the primary challenge that we have here is that macroeconomics are big, or macroeconomic models are big. Even the normal models we use are pretty big and take a while to estimate. And particularly as we move to heterogeneous agent models, they get even bigger. This number of states explodes. But we want to frequently re-estimate these models, and we want to re-estimate them, say, every quarter as new GDP data is released and other data is released. But we don't want to necessarily start from scratch every time. We want to use some of the information that we already had. And that's where this quote-unquote online idea comes in, that we already have some data, we have a posterior estimation computed, and we want to use that posterior and just update it. And that's one nice thing about SMC that we can do. Now, these are problems that many researchers face. We all want our code to be faster. We want it to be run in parallel. We want it to be somewhat adaptive and incorporate new data. And so you'll see some parallels that may apply to non-economic work as well. So in the past, we've used Metropolis Hastings to estimate our model to draw from this unknown posterior distribution. And Metropolis Hastings is really nice. Some of you may be familiar with it. And if you aren't, that's fine. I'll sort of go over the basic idea. Here you see that we draw some initial theta draw, which I'm going to call a particle, from, say, the prior. And in practice, we actually try and find the mode of the distribution using like a mode finding algorithm and start it from there. But say you draw it from the prior, and then you try and move to higher probability regions of your posterior. And you'll always accept higher probability regions, but sometimes you move to a lower probability region, and you might accept that with some probability also. And that probability is given by the Metropolis Hastings ratio that some of you may have seen before. And you end up with this chain of particles where you sort of construct this histogram that approximates the posterior. One note is this is just a single particle, and that will come back in a minute. So Metropolis Hastings has several shortcomings. First, this chain needs to be really long. You have to draw tons and tons of draws. You have to have a burn-in period where you like throw out the first couple of draws. You thin the draws so that because the draws are serially correlated and you don't want to take every draw because that introduces bad statistical properties. It's hard to initialize, so we have to use a separate mode finding algorithm and then compute the Hessian at the mode to give us like the step size covariance matrix. And you only have one particle moving around, so you can't parallelize it. And this is particularly true because it's a Markov process, so there's no, like, you can't parallelize it because where you go depends on where you're at. And then finally, what if you get stuck in a local mode? If you have some bimodal distribution that looks like this, and you're in one part of the distribution, unless your step size is huge, it's hard to bridge the gap in that low density region in the middle to get to the other side. So what we're now doing is sequential Monte Carlo. And this overcomes a lot of the shortcomings of Metropolis Hastings. Instead of a single particle, you have a whole swarm. This means that it's harder to get stuck in a local mode, but also it's easily parallelizable because the particles can all mutate independently of one another. You initialize from the prior, so you don't have to worry about the mode finding algorithm anymore. It's robust to multimodality. And then in this recent paper that we've just been working on in the past few months, we've also introduced an adaptive algorithm that will spend more time exploring the distribution and uses a finer approximation in new periods, in periods that are novel to the model, where data is very different from data that the model has seen in the past. And it will spend less time exploring the distribution in times when the data is pretty much the same as it's always been. We also have this online estimation feature where you can start from a previously computed posterior and then just incorporate the new data and update that posterior. And this can also be used to update a very simple model. So as long as your model has the same parameters, you can start from, say, a heterogeneous agent model that has a very coarse grid, get your estimation, see what kinds of results that model is producing so you have an idea if the model is even reasonable, and then refine the grid and use a much finer approximation, and then compute your estimation again, but you don't have to compute it from scratch. You can use where you left off. So to give you a sense of the speed improvements that just changing the algorithm has given us, with Metropolis Hastings, this is all in Julia, by the way. Metropolis Hastings in Julia takes more than a day to estimate just sort of a standard representative agent model, what we'd call a medium scale model. Switching to SMC reduced this down to 3 to 5 hours, and then switching to online SMC, where you have your estimation and then re-estimate it using where you left off, we can do this in 1 to 2 hours, which is pretty great. So I'm going to go over I've already gone over one of the building blocks of SMC, which is Metropolis Hastings, and I'll show you where that comes in a minute. The other building block is importance sampling, which some of you may have seen before, but the basic idea is that we have some unknown posterior, pi, and we want to use a different density, q, that we already know. So this is probably like a normal distribution or some easy to sample from distribution. So we just draw from this easy to sample from distribution Q, and then we want to compute weights that give us the relative likelihood of the draw under the posterior relative to how likely you were to draw it in the first place. So this looks something like this. You draw a bunch of thetas, which are your parameter values, from Q, and then you compute the unnormalized weights, then you normalize them, and any statistic of your final posterior distribution, given that you sample enough points, can be represented as a weighted sum of your draws, where the weights are given by this weighting of pi to q, your target density versus your proposal density. So I have these 3 distributions here. The black is the distribution that you're trying to sample from. Here it's like obviously a normal distribution. It looks easy, but in practice you don't know what this is. So you've tried 2 separate proposal distributions. You have the blue distribution, which is much closer to the black, and you have the teal distribution, which is much farther from the black. The teal distribution is a bad proposal density. So what happens when we sample from them? Well, we see this blue dot and the teal dot, and they're both relatively big, but the blue dot is even bigger because it's more likely under the black, this distribution you're actually trying to sample from, but you don't know. Well, we draw again. This time, you can't even see the teal barely. That draw was really bad. We were giving it a very low weight because it's incredibly unlikely under the black target distribution. The blue is a little bit farther out, but still a little bit more likely. We give it like a moderately sized weight. So we do this a couple of times. We fill out the distribution, and we see that in the end, we get a nice representation of the black with the blue weights, but the teal weights don't even get to the left part of the black distribution. So that's obviously a terrible proposal density. Now I've been showing you this in serial. I'm doing 1 particle at a time for the purposes of illustration, but in practice this can be done in parallel. You can just draw your particles at once and you get this representation of the distribution. So the point of this example is 1, to show the parallel part, and 2, to show you the importance of selecting a good proposal density. The question is, well, how do you choose a good proposal density? And this is where we start getting to the sequential part of sequential Monte Carlo. So sequential importance sampling, instead of just choosing a somewhat random proposal density, we're going to temper in the likelihood and use each time we temper in the likelihood as a proposal density for the next quote-unquote bridge distribution, and then have a whole sequence of proposal distributions that will eventually converge to the posterior that we want. So in the left plot here, we see a bunch of possible schedules, and all of them sort of have this concave sloping shape where they start off really flat, and then as you get farther on in the schedule, they slope up much faster. So this is the shape of our tempering schedule, and the idea is that when you start off, you have the likelihood to some exponent, and you want that exponent to be rather small. You don't want to include much information from the likelihood because that could sort of surprise your algorithm. You want to slowly incorporate the information from the likelihood and eventually temper in. So you started at 0, you continue going, 1e negative 10, very small number, 1.5e negative 10, that should be an exponent, obviously, another small number, but then you move on in the tempering schedule, and you get to n, and by this time your phi is still small, but it's gotten significantly bigger than it was at the beginning. You keep going, well now you're moving much faster because you've got into sort of this faster sloped part of the curve, and at this point you're increasing much more quickly your tempering parameter. So you end up, well, at the end you obviously want to include all of the information in the likelihood, so this exponent phi sub n should become 1. Okay, so I've shown you the 2 building blocks. The first one is Metropolis Hastings, and the second one is importance sampling. How do we combine them together into SMC, sequential Monte Carlo? There's 3 steps: correction, selection, mutation. In correction, that's basically the importance sampling stage. So we reweight the particles based on their weights. And in the selection step, we don't do this every time because if you do it too often, it can introduce noise. But the selection step means that you want to have the particles, a lot of particles in the parts of the distribution that matter, meaning the high likelihood or the high density parts of the distribution, and sort of way out in the boonies, the super unlikely parts, you don't care so much about sampling from there. So selection, you'll use systematic resampling, multinomial resampling to redraw the particles. And the mutation step, which is simply Metropolis Hastings. So we initialize the particles, they all have equal weights. We do a correction step where you can see that some of the particles are becoming bigger because their weights are bigger. We do a selection step, but here the algorithm has decided that there's enough particle diversity. It doesn't need to resample the particles, so we're not going to do it this time. We mutate the particles, and they sort of move around according to a Metropolis Hastings step. We do another correction step, and now you see that the particles in the middle are getting really big. That's probably where sort of the mass of the distribution is. And at this point, the algorithm has decided that the quote-unquote effective sample size has gotten too small, meaning that the particles we had too many particles that were very low weight out in the tails, and those are the parts of the distribution we don't care so much about, and we want lots of particles in the middle where we care more about seeing the exact shape. And so we say take a weight 100 particle and just make 100 weight 1 particles instead. So then we mutate them again, and while it looks like in the selection step they're all on top of each other, so you can't see like all 100 particles, but they sort of split out, and you see now that that's where all those particles went. And you repeat this over and over. So the algorithm, I've gone over all you need to know about the algorithm, but you initialize the particles, you compute their weights using basically the ratio of the likelihoods under the different proposal bridge distributions. You normalize it, you do a selection step, and you mutate the particles using Metropolis Hastings. If you really care about this algorithm, you can read more about it in the working paper, but I think the illustration is sufficient to give you an idea of what's going on. So the question emerges, well, how do you choose the phi schedule? How do you decide how quickly to incorporate information from the likelihood? And one proposal is to use a fixed schedule. That's what a paper by Herbst and Schorfeida did in the Journal of Applied Econometrics. And this is a really good approach, and it gives you this solid black line, which looks like the shape we want. We sort of slowly increase phi, and then near the end we increased a lot more. Another approach, which is what we do in this more recent paper, is an adaptive approach, where you choose a single parameter alpha that controls the maximum possible deterioration in your effective sample size. So we find the phis by basically just finding a 0, and we say we don't want the effective sample size to decrease by more than alpha, and if it does, that means we're moving too quickly, and we need to slow down the tempering, which is what's shown on the plot on the left, where those are all of the individual proposal bridge distributions, and the amount of distance between each distribution basically is how quickly the algorithm is moving. So this is the adaptive tempering schedule algorithm. That's the same expression as before. We say the effective sample size can change by at most alpha, and the effective sample size is given by the formula in the right, but the way you can think about it is basically the variance of the particle weights. And so you want you want the particles to be in parts of the distribution that matter, and you don't want those weights to get really big and have dispersed weights. You'd rather have a lot of particles that have more, not exactly uniform, but closer weights to each other. And that's the algorithm. Okay, so what happens when we do this in practice? We get this nice curve where we see that the fixed is strictly worse than the adaptive. It's both slower and less accurate. So on the y-axis here is basically accuracy. The MDD is the marginal data density, which is the likelihood of the data given the model. You don't need to know that, but we take the standard deviation of it, and that just gives a measure of how precise the algorithm is at always getting the same answer. So the fixed is less accurate, and it's also takes longer to run. But we get this frontier, which is shown with the lines, where as you increase alpha and you tolerate less deterioration in the effective sample size, you start off with big gains, but as you increase it more, the gains sort of flatten out. So the other contribution is the idea of online estimation, where you use draws from a previously computed posterior and then just go from there. So this can be used for having a data sample and then you extend the data sample. That's one approach. Or you can have a simple version of the model, so maybe a representative agent model, and then you add some heterogeneity to it. And as long as the model has the same parameters, you're fine. You just start off where you left off and then use that as use the posterior from the first estimation as your initialization, and then just keep going. A hypothetical example is, well, we have GDP data up until Q1 2019, but this Friday the BEA is releasing Q2 data. So we might want to re-estimate the model, and instead of starting from scratch, you can just temper in this new data and use our algorithm, which takes a lot less time. So here I show the formulas. The basic takeaway from these is all it amounts to is including a term for so T here is the whole sample and T1 is the shorter sample. So you just add a term for the whole sample and split that from the previously computed sample. And then you want to temper in, so phi goes from 0 to 1, the whole sample, and then temper down from the old sample. And then same thing for the weights, you just add an additional term. So how does this work when we do the same experiment with the online approach? Well, so the yellow curve is the online approach, and here we're not doing, we have our stopping period in 2007 Q2. So we go up until right before the recession and start our posterior from there. Well, what happens when you add in the recession period? That's not data that the model would predict. So you would expect for our algorithms to perform the worst when you're including recession data, which doesn't match anything the model has done before. So this is the worst case, but even in this case, the yellow curve shifts strictly to the left. So accuracy on the y-axis is basically the same. There's no meaningful story going on there, but it takes a lot less time to estimate. So this seems to work pretty well. We can do the same thing annually. So in the previous example, we went until 2007, right before the recession. That was period 1. And then we went post-recession. That was period 2. We can do the same thing every year. We go until 91, we temper in 92, we temper in 93, all the way up until the current data in 2019. So the top plot shows the marginal data density. This is how well the model fits the data. And as we would expect, all of the dots, no matter what your alpha is, are all the same. Because the model's the same, the data's the same, the algorithm should converge, so you would expect for this to always be the same no matter what adaptive schedule you choose. So that's great. But where we see the interesting action is in the preciseness of the algorithm, which is the standard deviation of the log MDD, and the runtime. So here, the blue is the sort of the worst tempering schedule, the 0.9, alpha equals 0.9. And that has a high standard deviation always, but in particular during the recession in 2008 and 2009. That's that spike there in the middle. And so what the adaptive algorithm is doing is during regular times, well, you have a finer schedule. Of course, the finer schedule will outperform the coarser schedule. But where it really shines is in novel periods, periods when data is very different than it's been in the past, because it can take more time there. So the runtime, of course, increases in 2008, but so does the preciseness of the algorithm. So a couple lessons that we've learned with parallelism from, because been a real ordeal, and we've gone from 2 workers, we've gone all the way up to 1,000 workers. And so we've dealt a lot with parallel, and special thanks to the Julia computing folks, Andreas and Matt, and also Chris Simmons at UT Dallas, who helped us a lot with this. So the first tip is to minimize data passing. That might seem pretty obvious, but what I have in this code snippet here is basically we're sending the model and the data to all of the workers in advance. And then our call to mutation, which is sort of cut off, there's more in that function signature, but we're only passing in basically the particles and a couple pieces of auxiliary information that we need to know to like construct the normal distribution for the Metropolis Hastings step and stuff like that. But all of the data that will remain the same for the course of the algorithm, we just tell all the workers in advance, and we never pass that again. Ooh, that's not good. Should I, yeah, I think I hit the cord again. Oh. Well, while this is coming back up, I'll tell you a little bit about network topology. Hopefully this will come up, but there's not too much more material that isn't on the slides that I can't just say. So network topology, by default, Julia will have an all-to-all connection. So all of your workers will be able to communicate with all of your other workers. And that's fine for some applications, but for what we're doing, we just have a master process and a bunch of workers that communicate with the master process. And the master process does sort of the correction steps that has to know about all the weights at once. But when you throw it off to mutation and the particles mutate independently, the particles don't need to communicate with each other. And so where this really makes a difference is in large shared clusters, where some of the nodes may not even be able to connect to enough nodes if you're going up to hundreds and thousands of workers. Ah, great. Thank you so much. So you can just set this when you add your procs and say master worker, and then you either will be able to add lots of workers, or you'll be able to add them in a reasonable amount of time so that you can like wait for all the workers to actually load and make connections with each other. Then the third recommendation is to simplify data structures. When we first started out, we were using a custom data structure that we made. We called like the particle cloud, which nested like some floats, some arrays, a couple other basic bit types. But we ran into issues when we started adding hundreds of workers. And we also experienced the dramatic slowdowns. And so we dug into this, and I mean, I'm no expert in this, but it seems like during serialization and deserialization, Julia tries to infer the type of the objects that you're passing to the workers. And sometimes it can't, because it dives into each recursive layer of your data structure, and sometimes it can't figure it out. So either it'll throw like a garbage, sometimes random structure, and you'll just get this random type error later on in the code, or it'll just be really slow because it has to loop through all these types. And so we just changed everything from our custom structure to arrays, and it was like miraculously fast. Julia is significantly faster than both the MATLAB and the Fortran. It's at least 2 times faster. This depends sort of on the number of workers that you use, how they scale, what model you use, and some of the models that exist in the Julia aren't the same as in the MATLAB, but the base case is it's at least 2 times faster. And the Fortran code was written by somebody who, we don't know Fortran, we didn't optimize it, but it was written by a co-author who knows Fortran well, so we would trust that it was pretty well optimized. So that sounds pretty good to us. And then the final point is, well, how does it scale? With a medium model, which, to give you a little bit of context, likelihood evaluations take less than a second. And that's the part you're parallelizing over, basically. So you're parallelizing over very quick tasks. It tapers off at about 100 workers. And that seems pretty good to us. Where we see real gains, and I unfortunately don't have a plot for this yet, is with the big heterogeneous agent models that Rika was just talking about. And that one we've gone up to 500, almost 1,000 workers, and we still see great performance because there the likelihood evaluations take a lot longer. So what's next? So we're planning on making a standalone package for SMC for any model. Right now you can estimate any DSGE model, any model that you write in our sort of way of writing models, which doesn't have to be a DSG model, but you just have to write it like one basically. But this algorithm can be applied to anything as long as you have parameters and you want to estimate those parameters using Bayesian methods, and you can specify a prior. This algorithm should work. So we're going to release, hopefully by August, a standalone algorithm for anyone to use. And then, of course, we're continuing to work on new heterogeneous agent models that rely on this SMC method to estimate. And we're also moving into nonlinear models that you can also use SMC for. And that's our interns are working on this project right now. So you'll see this maybe this will be next JuliaCon, we'll see. So thank you so much. And let us know if you have any questions or like you want to use this package in a certain way, because we don't really know how some of our models can be used. So feel free to email us with any questions. Thank you so much.
Start off myself. You said in the beginning, like, yeah, you have big models, but like, how do you quantify that, and like, how big are they?
Okay. So the best way to, one way to measure it is the number of states when you put it into state space form. And so sort of our classical bread and butter representative agent model that we're using for most tasks right now has about 45 states. It has probably like 60 parameters, and when we, so the parameters are obviously what we're mutating in any sort of Metropolis Hastings or SMC step. So that's one way of measuring it. You can also think about it in terms of, well, the number of states, because that affects the dimensions of your system matrices and the Kalman filter. So that's going to affect how long it takes to compute the likelihood. Or you could also think of it in terms of the length of your data. How many time periods you have, because that will also affect the runtime of the Kalman filter. So which of these is the best way to quantify model bigness? It's not entirely clear. I think time sample definitely isn't the best way, because the time sample, our data is relatively small. The computational time is mostly, I'd say, the explosion in states when you run the Kalman filter, or even to just solve the model. And also the number of parameters that you're moving around and exploring in this multi-dimensional space.
So am I getting it right that like this algorithm can be used more or less any time that like traditional MCMC algorithms are used? Like so like it's a competitor for Hamiltonian Monte Carlo?
Yeah, I don't want to. Oh, yeah, sorry. The question was if this algorithm can be used in any Monte Carlo question where you're sort of finding a unknown distribution, specifically Hamiltonian Monte Carlo. Is that right? So I don't want to like go way out of my expertise, but in theory, yes. It's a way of drawing from an unknown distribution. Yeah, in fact, you mentioned Hamiltonian Monte Carlo. One thing you could do, and this is sort of way out on the frontier project, is you could even replace the Metropolis Hastings step in the mutation step with Hamiltonian Monte Carlo, and this can give you some more, perhaps better properties. But yeah, it can be used for, in theory, any situation.
Exactly.
Exactly.